Okay, good evening, everyone. Due to a perfect storm of events, we are doing tonight's class via a recording. So this week, we're going to be looking at immunity, microbial disease transmission, and one other, I think, microbiology and disease that we need to discuss. Our culture plates haven't arrived yet. I was hoping they would arrive today. It's okay though, because we still have some time to work with. We may need to be pushing our microbiology, where we grow the microbes and whatnot, lab to next week rather than this week. I will still have an in-class activity to work on Wednesday, and I will just give you all instructions on how we're going to handle that. So when we talk about immunity, there are a number of factors that come into play when we're talking about a host that is susceptible to disease. Some of the definitions that have come in from the homework did define the word properly, but not quite to the extent that we need to. And some of that terminology I will be correcting as we go along throughout the rest of this module. One of the words that I was concerned with is listed in the homework list of words that we need, that you guys needed to define. And I will get to it eventually during the lecture here, so that everybody knows what that exactly means. When we talk about disease transmission, these diseases can come from nearly every member of the classification modules. So that would include eukaryotes, prokaryotes, viruses, viroids, and prions. There are 2 empires, 3 kingdoms, tree of life, and others. And we've talked about how humans have a fundamental, intimate, and complicated relationship with the microbial world, both internally and externally. And a lot of times we rely on our individual microbiomes or our normal flora to maintain homeostasis and to break down the foods into usable nutrient forms. Now, the bacteria that we carry with us require the same elements of nutrition that we do as an organism for energy and for reproductive purposes. And the application of this study to the control of diseases and other health problems, this is epidemiology. We study the distribution and determinants of health-related states or events, and epidemiology is a big job. As we learned during the first week of our module, all microbes do not cause disease, and we have seen epidemiologists from the CDC on down working on the epidemiology of the COVID virus. This is where we're going to study the way that things are spread, how we can prevent that, what are the signs and symptoms, what are interventions, before a person actually comes into contact with the microbe, and interventions afterwards as well. Let's talk about disease outbreaks a bit. This refers to groups or clusters of cases statistically above what would normally be expected in a given time period in a given location. We've seen, especially recently with the COVID, how the media has sensationalized and kind of blown the COVID thing out of proportion, but they had willing accomplices, the members of our ruling government party or governing party. Let's talk about different types of disease outbreaks. Now, if you look at figure 9.2 in your books, well, look at 9.1 first, because it shows a map explaining how maps are integral to the science of epidemiology and implementation of necessary public health practice. In this case, that they're talking about with this, it helped the eradication of smallpox, and we discussed that a bit. And then on figure 9.2, there's a map from 1945 revealing the worldwide distribution of smallpox and the countries in which it was endemic. So let's define what these words mean. Endemic diseases are diseases that are considered, let me word this a different way. Diseases that are considered endemic are those that are constantly present in a region, community, or population, but with the involvement of a relatively few number of people. The number of reported cases fluctuates, but the disease is never entirely eradicated. And you can see this in figure 9.2. The incidence of disease at a particular time depends on the following factors: the population behavior, percentage of immune individuals, environmental conditions, source of infection, the virulence of a pathogen or its disease-causing capability, genetic susceptibility of individuals. Now, one of the terms that I was concerned with was, what is a susceptible host? Yes, a susceptible host could be someone who is sick and their immune system is shot, so they're more prone to get a disease in that state. But when we talk about a susceptible host, there are a number of things that we need to take into account. Number one is the age of the individual. The very young and the very old are more susceptible to disease than people who are, in their 20s, between 20s and 40s. Lifestyle has a lot to do with susceptibility to disease. And a good example would be smoking. A person who smokes is more susceptible to disease because smoking damages the immune system, it damages organ systems, and it just makes one more prone to getting anything that comes along. The working environment also has a lot to do with susceptibility. If one works in an environment where there are lots of pathogens around or a lot of allergens or something like that, then of course they're going to be more susceptible to a disease than someone who is healthy. Nutrition has a lot to do with that as well. And we have talked about that in the past, and I'm not going to belabor the point here. Good nutrition is important. Exercise is important. This can make us less susceptible to a disease than if we didn't do those things. Now let's talk about an epidemic. Epidemic is defined as a disease that occurs with a greater than normal incidence of reported cases. Epidemic diseases typically reach a maximum and then rapidly decrease because the percentage of the population that is susceptible is eventually exhausted. Epidemics of typhoid fever, cholera, and dysentery are frequent in communities where sanitation practices are inadequate to prevent the spread of infection. And I actually got to see this, in living color in person when I was in Central and South America. A lot of the villages are built along waterways because water is life. Those waterways are contaminated because the people that live along them use them for everything from dumping sewage to washing dishes to washing clothes to even getting water for cooking. And there are a number of diseases that are endemic or epidemic to certain areas. Now, when we talk about a pandemic disease, this is an outbreak, and it's a worldwide event. It's typically a result of a new strain of a viral infection. The spread of cases is fast and crosses national and international borders easily due to 21st century globalization. We have a lot of travel by air, we have travel by sea, we also have travel by land that allow infected individuals to cross contaminate large groups of fellow passengers. And from there, those newly infected go on to infect their families and communities, and on it goes. In past centuries, pandemics were large epidemic outbreaks that spread with lower population numbers and larger physical distances between urban areas. They were mostly unable to reach the same numbers that pandemics of the past 100 years have been able to reach. Now, your book talks about the Spanish flu of 1918 and the HIV/AIDS crisis. The HIV/AIDS crisis began in the 70s and continues currently, but we have been witness to recently the spread of the COVID, and it's affected our schoolmates and maybe even family members. We've seen the damage that a pandemic can do to not only the health of a population, but also the viability of that population, or the ability for that population to work, to earn, to obtain food, to be able to pay bills, to go to doctor appointments and things. And we've seen that it's a difficult thing to deal with. And even with the interventions that were put in place, we haven't seen much of a difference between incidences of the COVID from state to state. Let's just look at states that were closed down completely. Take, for example, New York. New York City, Manhattan was closed down. California's been basically closed down. And their numbers are comparable to their disease numbers are comparable to those who did not shut down. So I'm not exactly sure that we understand how this disease is spread, because a lot of people who were locked down from the beginning ended up getting it. That tells me that we don't really know how it's being spread. Now, this is my own opinion from my observations, my readings, and my review of studies. So you can't quote that as pure gospel, but that's just my opinion. I've looked at outbreak numbers of deaths with this current pandemic between the states who completely shut down and the states who did not, and the numbers are comparable. In fact, in some cases, the numbers are higher in locations where they were locked down completely. So we could talk about that for years, I'm sure, and never come to a consensus. All right, let's move on to pathogens. Pathogen. What does that mean? This is just anything that is capable of carrying a disease. So humans can be pathogens. As you see on the list here, there are human carriers. Pathogen reservoirs are the sources or holding areas for pathogens. Now, I did talk to you guys about the difference between, well, let's talk about vectors to begin with. These are organisms that can spread disease from one organism to another. Okay, vectors could include mosquitoes, could include ticks. Flies are mechanical vectors. As you see, incubatory carriers are listed on there, and this is how some of these parasites, for example, have to be presented to humans before it can do any damage to humans. For example, the Anopheles mosquito is the one that carries the malaria parasite. The Anopheles mosquito is an incubatory carrier. That malaria parasite has to complete part of its life cycle within that vector before it can actually do any damage to humans. There are convalescent carriers as well. These convalescent carriers harbor a pathogen and can transmit it while recovering from the disease. The recovery period is referred to as the convalescence period. Cholera has a long convalescence period in which the person can carry the microbe for many months. Now, active carriers have recovered from the disease but harbor the pathogen indefinitely. And then passive carriers harbor the pathogen without ever having had the disease. Human carriers are responsible for the spread of staphylococcal infections, hepatitis, dysentery, and many sexually transmitted diseases or STIs, sexually transmitted infections. Inanimate reservoirs, we call them fomites. That would include air, soil, food, fluids. It could be water, milk. It could be our tabletops, hospital bedding, equipment, bedpans, skin. There are all kinds of secretions that can spread the disease. The methods of transmission, they can be transmitted from an infected person to a non-infected person in the following ways. Touching, this is direct contact. An infected person does not practice good hand washing techniques. This is a good example. Touches another person. Hospital staphylococcus infections in newborn nurseries are caused by healthcare workers because they're not following the policies. Let's talk about sneezing. Infected persons do not cover their mouths when sneezing or coughing, and the air droplets contain viruses or bacteria. Blood and body fluid contact is another one. And then there's indirect contact. That could include food or a fomite, which is an inanimate object that can carry a pathogen. Food prepared by an infected person, sometimes hepatitis A, and then contact with an animal or insect. So I think just about everything we come in contact with has the possibility of causing the spread of disease. Okay, let's move on to portals of entry. And we've talked about this in the past. The skin is the largest organ system of the body. And the first line of defense against pathogens. So it's part of our immunity. This is a non-specific defense that just defends us against anything that we can come up against. The sweat glands and hair pores of the skin may serve as portals of entry. There are some fungi that can grow on the skin or under the nails and cause infections. The larvae of the hookworm can actually penetrate the skin to become embedded. And boy, when that happens, that can travel anywhere within the body. When we talk about parenteral route, this is when the skin barrier has been compromised. This could be through a wound, an injection, cuts, bites. The parenteral, referring to the tissues beneath the skin, route for microbial invasion is established. The pathogens can then directly invade the underlying tissues of the skin and possibly penetrate further into the mucous membranes. Now, this is part of what's going on with my son. And I mentioned, I think in last week's discussion post, the terminal diagnosis that my son received about 3 months ago, due to what has happened to him with his surgical site infection. All of his essential organs are being destroyed. And there's basically nothing that can be done to help him other than make him comfortable with medications that treat symptoms. I think the whole process of going through the stages of grief, we as a family are still dealing with that, still trying to figure out I guess just the general response to this and how we should handle it as a family. So it's important that we do our jobs correctly so that these things don't happen, so that harmless bacteria don't get on the inside of a body and become opportunistic pathogens. The mucous membranes, these line the respiratory tract, gastrointestinal tract, genitourinary, and conjunctiva of the eyes. And there are a lot of pathogens that gain entrance to the body by penetrating these membranes. Most of the pathogens penetrate the mucous membranes of the gastrointestinal and respiratory tract. The respiratory tract is the easiest route of penetration. Pathogens can enter through the nose and mouth as airborne microbes, and they can travel on dust particles, moisture droplets. Some examples of diseases that are caused by pathogens that gain entrance through the respiratory tract include the common cold, pneumonia, measles, TB, smallpox, hantavirus, and I'm going to add the COVID virus to that now. The COVID-19 wasn't around when your book was written, so it's not included in there. Pathogens gain entrance to the gastrointestinal tract through contaminated water or food. If you've ever had food poisoning, you know well how that happens, and it's not fun. Most of the microbes that we take in are destroyed by the hydrochloric acid formed in the stomach or by the bile that is used for the digestive process in the small intestine. The pathogens that enter through this system could cause things such as hepatitis A, dysentery, cholera, typhoid fever, and giardiasis or giardia. That's a familiar one here in Utah if you've been camping up in the mountains, and there are some sources of water up there that people think are safe to drink, but they're full of giardia, which will cause severe diarrhea, and it's not fun. After pathogens have entered the host, they will attach to the tissues of the host. This is called adherence, and it's a necessary event for the process of pathogenicity and effective disease transmission. There are contributing factors to cause disease. The majority of pathogens must penetrate the host tissues. And these that you see on the screen are factors that aid the bacteria in penetrating the host defenses. Enzymes, the virulence of a bacteria is aided by the production of enzymes, exoenzymes, and these enzymes have various actions such as lysing, which means just destruction by enzymatic digestion. So they'll lyse cells and dissolve blood clots, intracellular substances. Bacterial capsules, sometimes they synthesize glycocalyx that forms a capsule around the cell wall, and that increases the virulence of the species because that capsule inhibits it inhibits phagocytosis. So the phagocytic cells, those are the ones that will eat the bacteria. It prevents them from attaching to the bacterium. So that's not good either. And then we have issues with cell wall chemical substances. The cell walls of some bacteria have these substances that increase the virulence. The cell wall of Mycobacterium tuberculosis contains chemical waxes that resist the digestive process of phagocytosis. We've talked about this a bit before concerning how these pathogens destroy tissue. They can do direct damage because it attaches to the host cells and it can invade other tissues of the body. Some microbes produce toxins that are dangerous to the host cells and tissues. These could be exotoxins, where the microbe will produce the toxin as part of its metabolism, and it's released as the pathogen is alive. The majority of the bacteria that produce exotoxins are gram-positive. These are proteins, many of which are enzymes produced inside the bacterial cell. And these exotoxins are effective in producing disease because they are soluble in body fluids and can easily diffuse into the bloodstream for rapid systemic distribution. Endotoxins happen when the bacteria die and the cell wall is lysed or destroyed. These are toxins that are kept within the cell as long as that bacteria is alive. But when it dies, the endotoxin is released to exert its effect. No matter what the species of bacteria, all endotoxins produce the same signs and symptoms. Could include fever, muscle, bone, joint aches, chills, and in severe cases, shock that could lead to death. And septicemia is the infection of blood. And basically, my son has septicemia, bacteremia. He has the bacteria in the blood that they cannot kill. So I've seen this firsthand. Let's take a look at immunity in general and herd immunity. So I am going to get out of this PowerPoint and we're going to watch these two videos that you see here. The immune system and vaccines and herd immunity. I think this is an important concept that we need to understand. So let's watch these two videos and then I will comment afterwards.
Hi, it's Mr. Anderson, and welcome to the Immune System Podcast. In this podcast, I wanted to start with a little history. These are some beautiful illustrations from the Florentine Codex, which is thousands of pages long. It was created over about 45 years by this guy, this friar, and basically what he did is he studied Aztec culture and how it changed over his lifetime. So we've converted a lot of this to English, and you can find some of it on Wikipedia. It's just fascinating. So you can see these rituals and these chieftains, and he would describe all of it. But a sad part of that is that he describes how smallpox came to and devastated the Aztecs. And it's one of the reasons why the Spanish were able to conquer them. And so they didn't have immunity to it, and that's what this is about. So basically what happens with any kind of an infection, a viral infection like this, is you have a virus, and that virus is essentially going to gain entry inside your cells. It's going to use the machinery of your cell to make copies of itself, and more copies of itself, and more copies of itself. And eventually, it's going to destroy the cell, and it's going to spread off to infect other cells. And so that seems awful. In other words, when you get a cold, what's happening is that your cells are making viruses, which are spreading to more cells. And if it weren't for our immune system, we would be devastated by all the viruses that are around us. And so we have to have protection. And so I like the analogy of a castle. A castle needs protection as well. And so if you're building a castle, you have to think about a few ways to defend yourself. First of all, you have to defend yourself from the outside. So it's good to have a moat. It's also good to have a really large wall, so it's hard for people to get over it. And this castle's great because it's got water on all sides of it. You also have to have soldiers, so if anybody were to ever get close to the gate, you could shoot them with arrows or pour hot tar on them. But if they were to breach the wall, you have to be able to fight them there as well. But probably when you're defending a castle, a more important thing is you have to have intelligence. You have to have spies that are sent out to surrounding areas to do reconnaissance and figure out what's going on, to recognize invaders when they come. And so I'm going to quit talking about castles, and we're going to talk about the immune system, but the same thing works inside us. And so the idea of a castle wall, let's start with that. And so what protects us from infection? Our castle wall is going to be our skin. And so what our skin provides us with is it provides us with a barrier. So there's going to be a barrier of cells, dead cells on the top, and keratin on the top. It's also going to have a really low pH, which makes it hard for any kind of bacteria to live there. And we're also going to have chemicals on the surface of our skin that are going to disrupt certain viruses, and also we're going to have bacteria that crowd out our skin, and so it makes it hard for other bacteria to gain entry. We're going to have what are called normal flora that just live on our skin. And so all of this is going to provide protection against infection. But occasionally you know that gets breached. Occasionally you cut yourself, or a pinprick or something like that gains entry. And so that would be just like the soldiers making it over the wall. And so what do we have? Well, we have a call to arms. We have inflammation. So basically we have chemicals that are released that cause our body to respond to that. Now, you constantly are being infected, especially if you're a teenager, because you get acne. So what is acne? Acne is essentially a infection in the pores of your skin. So it's bacteria that are living and feeding inside our body. And so how do we fight that? Well, we'll plug it up for one thing, but we have swelling. So we're going to increase the heat, but basically we're going to send soldiers in there. And those soldiers are the macrophages. Those are going to be the eaters or the big eaters. And what they're going to do is they're going to find anything that's not part of our body and they're going to eat it. So any invader is called an antigen. And so basically what a macrophage will do is it'll notice that this is not part of our body. It'll grab onto it. It'll take it into the macrophage. It'll secrete lysosomes and enzymes into it, which break it up. It'll lots of times present that on its surface, but eventually gets rid of it. And so this is an actual picture of a macrophage, and you can see it's grabbing, I don't know if it's viruses or bacteria on either side. And so that's great. But the one thing about it is that it attacks anything that's not us. In other words, if you get a heart implant from someone else or you get a heart transplant, those macrophages are going to attack it as well. It's going to kill that. And so we also have what's called a specific immune response. Specific immune response is more like the spies. And so basically, here's an antigen again. An antigen is going to have specific proteins on its surface, but to fight that, we use what are called antibodies. And so the name antigen means an antibody generator. In other words, it generates the formation of antibodies. So what are antibodies? Antibodies are going to be proteins produced by our body. And basically, they all look the same. They're this Y kind of a shape. So they're a Y shape like this. We produce almost an infinite number and an infinite variety of them. But at the top of the Y, you're going to have different shapes. In other words, you're going to have a shape that looks like this, but you're also going to have an equal shape that might look like this. And you're going to have an equal shape that might look like this. And so we're going to have all of these different shapes at the top, but we're only going to produce the shape for the one thing that we're infected by. So basically, the antibody will dock to the antigen. And when it does that, basically it marks the antigen so macrophages can find it. And it also makes them harder for them to do their job. Imagine if I had another antibody here and another antibody here and another antibody here. It's hard for them to do their job. And so when you gain immunity, specific immunity or specific immune response, what that means is you have the ability to produce these antibodies. And that's why when you have a cold, you're not going to get that same cold again. And so basically, how do we do this, or how does this work? Well, we need what are called lymphocytes. Lymphocytes are a type of white blood cell. And so basically there are two types of lymphocytes. There are B lymphocytes and then there are T lymphocytes, which we'll get to in just a second. Okay, so B lymphocytes are made in the bone marrow, and they're responsible for a humoral response. Now this term I'm going to show you a couple more times in this podcast. Humoral means in the fluid or in the humors of your body. So that means in the blood, in the lymph material, in the lymph vessels, in the interstitial fluid. And so humoral response, what I want you to think about, is going to be anytime there are viruses free in the fluids of our body. And what the B lymphocytes do is they produce antibodies. So how does that work? Basically, you have a naive B cell. It's going to sense the shape of the antigen. I'll tell you how that works in just a second. But basically what it's going to do is it's going to produce antibodies. And so what B lymphocytes do is they produce all of these antibodies that are specific for the antigen. So in other words, if we're infected by this virus, we'll call this virus A1, then we're going to produce antibodies for that specific antigen. We're also going to produce memory B cells so that we have that immunity for the rest of our life. So those are the B lymphocytes. And so you might think, if they attack the viruses out inside our body, then what do the T lymphocytes do? Well, the T lymphocytes are responsible for cell-mediated response. What does that mean? They're going to target and kill the cells inside our body that are already infected. Okay, so what are the T lymphocytes? Where are they made? They're made in the thymus gland, which kind of sits on top of our heart. Basically what they do is they create what are called killer T cells or killer T lymphocytes. And so a killer T cell is an activated T cell. Basically what it'll do is it'll find any of the cells inside our body that are infected with a virus, it'll dock next to them, and it will kill our own cells. And so it's going to kill any of the cells inside our body that are infected by the virus, or even cancerous cells, it's going to kill them. And so it's made in the thymus, and it produces cell death inside us. And so the T lymphocytes are responsible for the cell-mediated, killing cells inside our cells that are infected. B lymphocytes are going to be in the humors of our body. And so if I were to summarize this a little bit, this would be the humoral response up here. So what type of cells are responsible for that? Those are going to be the B cells. And here's the cell-mediated down here. Those are going to be the killer T cells. And so before we get to that, let's look over here on the left side. So basically what's happening, we've got an antigen that is eaten by a macrophage. That macrophage is going to chop up that antigen. It's going to present pieces of it on its surface. And so we use a chemical called a MHC2. It's major histocompatibility complex 2. It's going to present the shape of that antigen on its surface, and now we get this cell right here, which is super important. It's called the T helper cell. What the T helper cell is going to do is it's going to dock and it's going to physically sense the shape of that antigen. It uses another protein called CD4, and it's going to sense the shape of that antigen. The helper T cell is responsible for initiating both the humoral and the cell-mediated immune response. So let's see what helper T cell is going to do. Helper T cell is going to tell that shape to the B cells, and so it can produce more antibodies. It's going to activate macrophages, so it can kill more of them inside the humors of our body. So it's responsible for that humoral response. And the helper T cell is also going to activate the killer T cells, so they can kill the cell-mediated, the cells that are infected by a virus. And so if it isn't for these guys, if it isn't for the helper T cells, we're out of luck. Now, sadly, helper T cells are the cells that are infected by HIV or people who have AIDS. And so you can see why that's a really bad thing, because without the helper T cells, we can't fight normal infections. So if you have HIV, you don't die of that, you're dying of normal infections that we would fight off. So let me kind of do this in cartoon style if we were to animate it again. So what we've got here is our antigen. Remember, that's our invader. And so basically what's going to happen is it is going to be eaten by a macrophage. So the macrophage will take it in. It'll secrete enzymes into it, which are going to digest that antigen. It'll get rid of it, but it's also going to grab onto a little bit of that. It's going to grab on with this major MHC. It's going to take its shape out to its surface, and now we have helper T cell. What's helper T cell going to do? Helper T cell is going to dock with that macrophage, and it's going to sense the shape of that antigen. It's now going to become an activated helper T cell. So thinking back to that flowchart just a second ago, where does it go next? Well, it can activate macrophages, but more importantly, it's going to activate B cells. So now we've got an activated B cell. It's going to activate killer T cells. And now, through clonal selection, it's basically they're going to make clones of themselves. We're going to have a whole bunch of activated B cells. We're going to have a whole bunch of activated killer T cells. So now, thinking about it, this on the top is going to be the humoral response up here, and this down here is going to be the cell-mediated response. And so basically, we can fight those antigens out here in the humors of the body. We do that by sticking antibodies to it so macrophages can eat it, break it down. We also inactivate them a little bit. But if you look down here, that killer T cell is docked with a cell inside our own body that's already infected by an antigen. And so it's going to secrete enzymes into it that are going to break that down. So it's going to kill that. And so basically what we've done is we've killed them in the humors or in the fluids of the body, and then we've killed cells that are infected. And so this takes a while, but it's going to be your immune response, and it's specific to that antigen. Until we get that specific antigen, we're not going to produce the antibodies for it. So let's talk about a cold, because I'm getting a cold right now. So basically what happens is you're exposed to the cold right here. The virus is going to start reproducing inside my body, and it's going to take me a little while for me to start building B cells and killer T cells. And so there's going to be a lag time, but essentially I'm going to produce a whole bunch of antibodies and effector T cells. So that's going to increase inside my body. And this time right here is where I actually feel like I have a cold. So this is me feeling like I have a cold. But really what's happening is it's my body fighting and killing off all the viruses. And so let's say I get exposed to that same cold again in the future. Well, in the future, I'm going to get exposed to it. But since I have so many antibodies, I'm going to produce them so quickly. And since I have these memory B cells and memory T cells that are just hanging out, I'm going to fight off and kill that infection before I even realize that I have a cold. And this could be years later. Now, how could colds get around this? And they do get around it. Well, they can have a bunch of different types, and colds, I think, have 100 different types of rhinoviruses. But they also can mutate, and if they mutate, they change the shape of the antigen, and now those antibodies aren't going to work anymore. And so that's the immune response. If you think of it this way, it's like keeping the invaders out of the castle. You're at least one step closer to understanding the immune system, and I hope that's helpful. Most people are familiar with vaccines and how they offer individual immunity against a disease, but they might not understand how the people around us or our herd offers immunity to everyone in the herd. A herd is a group of mammals that are living together for protection, maybe protection against lions in Africa or wolves in North America. But how does that apply to humans and disease? Well, let me show you a little model I put together. So we have these individuals in a herd, and let's say one of them gets sick, and the infection rate of this disease is 50%. There's a 50% chance you could pass that on to another individual. So this person is in close contact with 1, 2, 3 individuals, and so I simply flipped a coin. Heads you get sick, tails you don't, and 2 of the people got sick. I then took those individuals and flipped coins for the people around them, and this person, for example, infected 1 individual, and this person infected 2. And then I just kept doing that over and over and over, and you can see how the disease spread through the population. Now, how quickly a disease spreads through a population is based on how many people you can infect, and we call this the basic reproduction number. What is that? Well, for this individual, they infected 2. This person infected 1, this person infected 2, this person infected 0, and if I take a number of those individuals and find their average, that's going to be my basic reproduction number, or R0. If R0 is ever less than 1, in other words, you can infect at least one other person, then the disease dies out. But if you've ever heard of a disease, that means its R0 value is going to be greater than 1. And here's some R0 values for some diseases you might be familiar with. So the recent outbreak of Ebola, R0 value 1.5 to 2.5, smallpox 5 to 7, but some diseases like measles and whooping cough, the R0 value might be as great as 18. That's because it's an airborne transmission. And so what happens after you get a disease? Well, you get sick, and in some diseases you might even die. But if you know anything about animals, we can gain immunity to that disease. Once we've got the disease, we're not going to get the same disease again unless it mutates highly. And so what these people with immunity do is they offer protection to everyone else within the herd. So let's see that disease comes in again, and it starts to spread through a certain part of the population. Well, the rest of the population can't get it because these people with immunity offer a fire break or a firewall against that disease spreading into the population. And so once our herd gets large enough, like this, even though a lot of people don't have individual immunity, they have herd immunity. So let's say a person like this comes in who's sick, they're surrounded by so many individuals who are immune that the disease can't spread to those who are susceptible. And so the problem with this is you have to get sick, or you have to have members of your population die for you to get this herd immunity. But science has come up with a solution to that. It's called a vaccine. We give you a weakened or a dead version of that disease, and then you can gain immunity to it. And so that's wonderful. And you might think, let's go back to that model again. Let's simply vaccinate everybody. If we vaccinate everybody, everybody has immunity. But we can't vaccinate everybody because it's a voluntary process to get vaccinated. Some people don't want to. You shouldn't get like a measles vaccine if you're a baby or you're a pregnant female. And then as you get older, you may lose some of this immunity. So not everybody can be vaccinated. It just simply doesn't work that way. And so what scientists have come up with is a herd immunity threshold. What does that mean? It's how good is good enough? What percent of our population do we have to have vaccinated or immune to the disease so we all get this herd immunity? Well, it's going to depend on the R0 value of the disease. So if it's something like mumps with an R0 value of 4 to 7, we have to have at least 75 to 86% of the population who is immune, so the whole herd can gain immunity. But as those R0 values get greater and greater and greater, like 18 in measles, we have to have 94% 50% of the individual's immune. And so as people decide not to get vaccinated, what's going to happen? We lose that herd immunity, and we're going to have outbreaks of disease. So if you live on the plains of Africa, you're protected in a herd against a predator like a lion, but who is the lion that's stalking us? It's the disease, which is hiding in other individuals around us, but we also now have to worry about the individuals around us. Are they immune? Are they vaccinated? If not, they're not only putting themselves at risk, but they're putting the whole herd at risk.
Okay. So that kind of explained general immunity and then herd immunity, where I think that's what we're trying to reach right now with the vaccination procedure that's going on right now for the COVID. Each year we're vaccinated against the flu, or it's made available to us anyway. All right, let's see where we are here. Okay, now I'd like to talk a little bit about controlling microbial growth. There are numerous ways in which pathogenic microbes can be managed or controlled. As we learned with the last chapter, our first line of defense is the human body. We have external and internal barriers presented by the skin, mucous membranes, and secretions. And these barriers are part of the innate immune system. The second line of defense would include blood and chemicals. So we already talked about phagocytes. These are the white blood cells that run around and eat microbes or any other antigens. There are blood proteins, interleukins, and interferons. Fever, which is part of the healing process, and the inflammatory response. I think I mentioned before that microbes are very sensitive to temperature. I remember back in the old days, we had an idea that microbes couldn't live in extreme environments. So we didn't think that there were microbes within lava flows, for example, or in extremely high saline waters. So since then, we found out different. There are microbes that love hot areas. They live in the hot spots in Yellowstone and various other really hot places. We call them thermophiles. They love heat. Those who love salt are called halophiles or halophiles because they love salt. Now, if they're extreme lovers of these things, for example, somebody who loves extreme heat, some organism might be called an extreme thermophile. So as microbes are sensitive to temperature to a certain point can only slow down the reproduction of these microbes. Sometimes we can use high temperatures to destroy microbes, and that's where our autoclave comes into play. The autoclave is designed to destroy all living matter on anything that's put inside of that autoclave. That could include fluids. It could include drapes, such as drape cloths. It could include instruments and medications as well. Let's talk a little bit about immunity. There is adaptive immunity. This is passive adaptive immunity. And I think Mr. Anderson covered that really, really well in the videos. Now what I'd like to do is have you guys look at, let me find it here. A short episode from Monsters Inside of Me, Monsters Inside Me. This is the botfly larva, and the reason I'm sharing this is because I did have an experience in South America with this one. One of my guys actually had a wound on his leg that I couldn't figure out. It kept weeping. It was open. It was very painful. And we ended up figuring out with the help of a curandero or a witch doctor that it was a botfly larva inside of his tissue. So let's watch this short video regarding the botfly. So just a little short video of what it looks like when it's inside of the flesh. Usually what happens is these eggs will be laid in clothing. It could be laid on skin as well. Usually what happens is they lay their eggs in the clothing, and then of course that kind of irritates the skin once the clothing is next to the skin, and then the victim scratches that and ends up opening up just enough for that egg to enter and turn into a larva. And the botfly larva will stay in there and just eat all of the flesh that's surrounding it. I think I just muted myself again. Anyway, it eats all of the flesh and it causes a lot of pain. Okay, we'll watch this one because I think this one's going to give us a better idea of what it is.
The botfly is a hairy insect about twice the size of a housefly. Its maggot larvae are known to live as parasites in human flesh.
Botflies only have a few offspring over the course of their lives, but they're very careful about where they place them so that those offspring are more likely to survive.
Skin provides food and shelter for baby botflies, and the botfly larvae are brilliantly adapted to living in the flesh of another organism. Botflies have special mouthparts that allow them to burrow into their host's skin. At the maggot's rear end is a breathing tube that keeps the larvae supplied with oxygen while it's in the skin. The doctor can see the botfly maggots through their breathing tubes, which form holes on the top of each bump.
To complete its life cycle, a botfly has to find a way to get its eggs onto the skin of a host. But the adult botfly has a problem. It's too big and conspicuous to drop the eggs off for itself. So what it does is it uses a mosquito to deliver the eggs for it.
The female botfly ambushes a mosquito in mid-flight. The botfly lays its eggs and glues them to the underside of the mosquito. When the mosquito lands on human skin, body heat melts the glue. The eggs fall off the mosquito and hatch into larvae, which burrow into the skin. If they are undisturbed, they will remain there for 6 weeks. Eventually, the larvae crawl out through the breathing hole, fall off the skin, and burrow into the ground. 4 weeks later, they emerge as adult botflies.
Because botflies only make a few offspring, they need those offspring to get where they need to go, and that's why using a mosquito is such a brilliant strategy. Botfly larvae are ringed with little tiny black spines, and those are there so that if you try to pull it out, it's going to get lodged into place. It's a great way to make sure that it doesn't get pulled out by the host.
One way to extract a botfly is to cover the air hole, starving the maggot of oxygen. When the cover is removed, the maggot surfaces and can be extracted safely. To avoid hosting a botfly, keep away from mosquitoes when in the tropics. Always use insect repellent and cover up at dusk.
To complete its life cycle, a botfly has to find a way to get its eggs onto the skin of a host.
The botfly's cunning reproductive strategy ensures more of its young survive.
That was just an example of what monsters inside me can show you. And I found out that this was on the, I think the series is running on Discovery Life channel. And there are a bunch of full-length episodes that you can watch on YouTube as well. And that's as far as I'm going to go with that, because I thought that it was on Netflix also, but I'm not sure. So I'm not going to commit to that. Now, what happened with the guy that I knew that had this wound, I didn't know what was. We were finally talked into going to the witch doctor, and I'd gone in. This was one of my first encounters with the curandero in South America. And I basically just took him to the curandero just to keep everybody around me quiet, because everybody in the village kept suggesting, oh, send him to the curandero. He'll be able to cure him and whatnot. Well, I relented and took him in. And well, as soon as my buddy pulled his pant leg up, this curandero says, oh, I can take care of that in a minute. And I'm thinking, yeah, right. What are you going to do? Do some kind of magic ceremony to get rid of it? You know, that's how I thought of curanderos at the time. He actually reached up above him on a shelf and got some petroleum jelly, Vaseline, and he spread it over the hole that was in my buddy's leg. Now, in my mind, it was the dumbest thing I'd ever seen done. But it didn't take long before that little botfly larva poked his head out because he'd run out of air. The petroleum jelly had cut off all of the oxygen or the air for this organism to survive. And when the botfly poked his little appendage out, whatever end of it was, probably the back end of it, the curandero reached over and just kind of squeezed it like you would a zit. And that botfly larva just popped out and shot right across the room. So we were able to get rid of it that way, and he was able to heal up rather quickly after that. You know, once the larva was gone, it was fine. What we need to do is, I think, be aware of what's going on around us when we're in a surgical setting, when we're in a classroom setting. We need to make sure that we pay attention to asepsis, because we don't know, you know, how susceptible maybe one of our classmates might be, or maybe one of our administrative people might be. You know, there are a lot of factors that we need to take into account when we look at susceptibility to disease. And age is one of them. And I will tell you, the very young and the very old will catch a disease quicker than somebody who's young and healthy. So let's keep that in mind. Let's remember to wash our hands when we're dealing with the bacteria, either this week or next. It'll probably be next week before we get our supplies. But let's be careful. Let's keep the principles of aseptic technique in mind. We're going to keep our countertops, our tables, our hands clean. We're going to use our personal protective equipment. Now, I do also have another announcement about our end of mod party. We're going to combine with the other Surge Tech class, and it looks like we're going to have a taco bar. If there are any changes to that, I will let you know ahead of time, but that will be on the final Wednesday of the module, which is a week from this coming Wednesday. So I will give you more updates as to what will be happening during Wednesday's class. Please remember to get your discussion questions answered early in the week so that we have time to respond to that. If you guys have any questions or issues, let me know. I'm available for you anytime to help with homework, catch up with anything you need caught up with, or even further instruction. And then I have another announcement that I will put in the announcements regarding some additional help for your classes in your career. So I'm going to end tonight's session at this point. Please read chapters 9 and 21 in your book, in your textbook. And Wednesday, we will continue. Hopefully, some of us will be back in the lab at that point. Either way, I will make sure that everybody gets to participate in every lab, despite what's going on, you know, with illness and whatnot. So get a hold of me if you need any help. If not, I will see you guys on Wednesday. And please watch the announcements. Thanks for joining me.